Hi, I'm Antonio Sala, and in this second video of the Hidden Tiger case study, we'll delve further into the interpretation of marginal, conditional, and joint probability tables. If we recall the problem we were studying, we had a zookeeper that had to decide which door to open based on where the tiger roaring is heard with greater intensity, either at the left door or at the right door. So, the moment the central gate closes, tiger may be either left or right. And then, depending on whether tiger is right or left, we will hear roaring left or roaring right with different frequency, let's say. So we have two binary random variables and we were modeling the interaction between them. In a previous video, we posed the problem by first stating a conditional probability table, such as the one here below, saying that if the tiger is at the left cage, then 80% of the cases will roar towards the left door, but 20% will roar towards the corridor, and we will listen to it at the right-hand side door, and likewise for the tiger right conditional probabilities. And in order to build that joint probability, we consider 4 atomic events, let's say, the 4 combinations of tiger left-right, hearing, roaring, left-right. We actually wished to arrange them in a 2x2 matrix, so we keep the structure of 2 interacting random variables. And from this formula that defined conditional probability, saying that it's the number that multiplied by the prior or marginal, we'll delve on it later, probability, gives me the joint probability, then if we named B as the prior probability that the tiger is at the cage at the right hand side when closing the center gate, well then, if that is B, it will be at the left with probability 1 minus B, and then the conditional table can be multiplied by this probability of tiger being at either side when closing the gate, so we would obtain the joint probability. If I execute with 0.9, believe that tiger will go to the right because, food is always served at the right. In that case, multiplying the conditional, this column times 0.1, this column times 0.9, got me the joint probability for numbers that add 1. What we will discuss in a minute in this video is that, the only mathematical object we need is the joint probability, the probability measure, some stuff that adds 1, and from that stuff we can deduce everything. But physically, or in an engineering viewpoint, it's convenient for us to, let's say, decompose the tiger problem into 2 steps. First, step 1, close the gate, and then we have some probabilities of tiger left and tiger right, and then step 2, tiger roars, with some probabilities of here left and here right conditioned to wherever tiger is. Then we can build the joint probability with that. It's the only mathematical object formally needed, but this kind of decomposition is very helpful in engineering modeling, let's say. Basically, divide and conquer, decomposing complex problems into simpler ones helps us getting a better insight on what's happening. So this 2-step procedure gave us this joint probability table, and now we'll see that we can indeed recover those steps from this joint probability table. So all required information is in the joint table. We'll recover the probabilities of tiger lefts and right, which will be called marginals, and of course we will recover the conditionals. But we'll recover some other things which will be of great interest. Let's see. We'll first compute or extract what we call the marginal probability distribution. What do we understand by marginal distribution? Well, let's see. Let us first do the computation, and if we have this joint probability table, I label columns and rows to understand what it was. Then if I sum the columns, I get 0.1 and 0.9. That's what the sum command does in MATLAB, summing the columns of a matrix. So we recovered the 90% probability of Tiger being right we were discussing a minute ago. So we used the conditionals and 0.9, 0.1 to build the joint probability, and then by summing the columns, we recover the so-called marginal probability of Tiger state. Indeed, if I have 4 atomic disjoint events, 4 combinations of these random variables, if I sum probability of all the occasions in which Tiger is left, then okay, these 4 numbers add 1, but in 10% of the cases the Tiger will be left, and in 90% of the cases the Tiger will be right. So even if in our problem statement first video this 0.1, 0.9 was kind of a datum from my physical insight and decomposition on 2 stages of my problem, I can get it as a result from the joint table. It doesn't mind what's first. I mean, all tables and probabilities are interrelated, and in each problem I will take decisions regarding modeling on which things are known and which other things are computed from those known data. Well, the thing is that summing by columns, I get what we call the marginal of the Tiger location state, and summing by rows, I get what's called the marginal for the here left, here right random variable. Indeed, I have 4 possible events, so if I add the probability of all the events in which I hear something roaring in the left door, well, then that's the definition of the marginal, you know. Of course, I can decompose it in 2 sub-events, here left when Tiger is left, here left when Tiger is right, but okay, if I am only interested in the frequency in which I hear roaring tigers at the left door, then it's 17%, period. So, if I have a joint probability table, summing rows or summing columns gives me 2 different marginal distributions for considering each of the random variables separately. Of course, the interaction is encoded in the 2 by 2 table, but I can disregard such interaction. So we get 2 marginals. Good. Let us now think in recovering the conditional, which, well, will be easy just from this definition of conditional. It is the joint divided by marginal. Let's see in our example. If I have here the joint table repeated for convenience, I repeat the marginals also for convenience, 0.1, 0.9, and sum by rows. We'll discuss it later on. Well, then, the conditional is the joint divided by the marginal, so it is kind of dividing this, each of the elements, of course, by 0.1, which is the same as multiplying by 10, of course, in this case, so I get 0.8, 0.2, which was the 80%, 20% conditional table I started my problem with in the first video. And if I divide this column by 0.9, then I get 0.1, 0.9 as the conditional of what? Well, we know it's here given Tiger, so this is, say, the conditional here right given that the Tiger is for sure at the right, this is here right, Tiger left, etc. But how do we assess this meaning from this joint table? Well, this 80% is the fraction of the events in which tiger is left and I hear left, divided, by the total events in which the tiger is left. So 80% of the times tiger is left, I will hear left, and 20% of the times tiger is left, I will hear right. So this column divided by its sum is the conditional. Each of the elements has the units of hearing, and the condition is the label of the column I am adding. So these are conditional probabilities conditioned on tiger left, and when I operate on the second column, then the condition is tiger right. So what we did is, reversing the steps we used in the first video to build the joint table. So we used the prior in here called marginal and the conditional to decompose my problem into two sub-problems, and then suitably multiplying them, I got the joint probability, and in here, suitably summing and dividing, I revert my steps and get the marginal 0.1, 0.9 and the conditional I started with. Good. So, as I said, everything is in the joint probability. But, well, as we have a second marginal, this one we were saying we will discuss later on, now it's the moment, then if we have a second marginal, then what would be dividing this row, by the sum of the row? Well, mathematically it would be exactly the same thing we have done with the columns. Sorting which is 1 or 2, or whether we put tiger in columns and hearing in rows or vice versa is just arbitrary, so there is no mathematical problem in saying, of course, we can do that, and it will have the exact same meaning we had with the conditional of hearing given tiger. But well, the first one was reverting our steps of the first video, so what's this second one? Well, let's compute it and speak about it for a while to better understand what's its meaning. So, let me label it again. If I divide the joint rows, each of the elements, by the sum of the row, the marginal, I get this conditional. Then, interpreting what this table means, for instance, this 0.97 will be the probability of tiger right conditioned to hear right, because I am summing by rows. The marginal was the marginal of hearing, so in the conditional probability definition, if the marginal was hearing, then the condition is hearing. So this means that with my table, 97% of the times I hear my tiger roaring at the right hand side door, it will mean that the tiger is actually at the right hand side cage. Let's discuss another numbers. This 53%, let's say, will be the probability conditional, of course, conditioning to hear left of tiger right. What's this? Well, it means that 53% of the times I hear roaring at the left door, my tiger will be at the right hand side. Come on, how is it possible? Well, remember that when we were building the joint table, we assumed a prior probability when closing the central gate of the tiger being 90% of times at the right side, because, food and mating partners are there. So by default, we will tend to think that most of the cases tiger will be at the right. If I hear something at the left, well, I will assume that it is quite likely that it is actually on the right cage, but roaring through the corridor. The actual formula, gives me 53% of the cases in which I repeat the experiment of let the tiger go left, right, whatever, with the central gate open, close the gate and lock it, and listen to roaring. Then, even if I used the other conditional and marginal to build my probabilistic model, now I can say that from the joint probability, 53% of the cases in which I hear noise at the left, tiger will be at the right. Let us look at the joint table just for a last confirmation, so that indeed what we are doing is 0.09 divided by 0.17, which is 53% of the cases. So if I am sure that the thing in the top row has happened because I did listen roaring noises at the left door, okay, then 53 of the cases will be caused by tiger being right, roaring to the corridor, and the remaining 47% will be caused by tiger actually being left, roaring to the door. But that second case is very infrequent, 8% of total, so 9% wins. Well, this is the second conditional. So this is the formal interpretation from the joint table. What about the physical interpretation? Well, the thing is that in the first conditional we had this kind of table, and now we are considering the reverse table. As I said, from the joint probability we can compute both, because for MATLAB, column 1 or 2, row 1 or 2, or switching columns and rows or whatever, is just an arbitrary choice I made when building the matrices, so the same operations can be carried out by rows or by columns. But this first one had, physical meaning. This was the cause and this was the effect. And I decomposed my problem into building a probability of the cause of the tiger location, marginal, non-conditional, and then building a conditional probability table of the probability of a given effect given a location of the tiger. However, that physical meaning is absent from the second conditional probability table. I mean, hearing the roaring noise is not the cause of the tiger location. So the physical meaning is sort of reversed. Does it mean that it is somehow incorrect? Not at all. I mean, we are counting percentage of cases. Computations are perfectly good. But, counting percentages, probabilities of things, and grouping them in some groups or other groups, that's perfectly valid. But some of the ways we group the stuff have a physical cause and effect interpretation, and some others do not. So the wrong physical interpretation would be that, the tiger listens to some noise and then decides which side to go. It's not true. We reversed the causality arrow, let's say. But, that inverted causality is the thing that the zookeeper will do. The zookeeper will wait till he listens 1, 2, or 5 roarings at the left or the right, and then he will decide where to go. So somehow the first is used in the modeling, cause and effect relationship, decomposition of my problem, and the second is used for actions. This is what we call estimation of this kind of probability we are obtaining here, or we'll delve into it in the next video. We use this second conditional to build what we call posterior probabilities. My zookeeper indeed will first think that tiger may be half, right, left, who knows, and then after listening to a couple of roars on the right hand side door, then we will change its belief, and then he will think that tiger must actually be at the right. So this change of my credence belief on the tiger location based on what I hear will make use of this second conditional probability for estimation and decision. But for the, let's say, physical modeling of my problem, the easiest way to go was this conditional probability and the probability of tiger left or right in order to build a joint. But once I build a joint, I can of course reconstruct this one, not too useful because I started with it anyway, and reconstruct the second marginal and second conditional, which indeed will be the core of what is called Bayesian inference and Bayes' theorem or Bayes' formula. We will discuss that Bayesian stuff in the next video. In here, with the review on the interrelations among joint, marginals, 2 of them, and conditionals, 2 of them, probability tables, we end up here. So, thanks for watching.